12,500 years ago, something happened that changed Earth faster than anyone expected. Ice melted, oceans rose, winds shifted, and the climate flipped direction in a matter of decades. Greenland stood at the center of it all, quietly recording every moment in its ice. In this documentary, we follow that frozen record step by step. From sudden temperature drops to massive meltwater floods, from disrupted ocean currents to shifting skies filled with dust, and from human survival at the edge of the Arctic to the scientific debates that still continue today. This is not a story of myths or guesses. It is a real investigation into what Greenland reveals about Earth's most dramatic turning point and why it still matters now. Chapter 1. Greenland before the ice we know today. When people picture Greenland today, they imagine a land locked in ice, a white mass so large it can be seen from space. But this frozen image hides a much longer and more complex story. Long before the ice sheet reached its modern size, Greenland looked very different. Not tropical, not lush, but alive in ways that surprise many people who first study its past. To understand what Greenland was like before 12,500 years ago, scientists do not rely on myths or legends. They rely on ice. Not just the surface ice we see today, but ice drilled from deep below, pulled up in long cylinders called ice cores. Some of these cores reach more than 2 miles down, passing through layer after layer of snowfall that hardened into ice over tens of thousands of years. Each layer is like a page in a history book, recording temperature, wind, snowfall, and even the chemistry of the air. The deepest Greenland ice cores, such as those taken from central Greenland, reach back over 100,000 years. When scientists analyze these layers, they find that the ice sheet did not grow in one steady motion. It expanded and retreated many times. During warmer periods of the last ice age, parts of Greenland were less icy than they are now. In some regions, glaciers pulled back. Rock and soil were exposed. Plants adapted to cold climates could grow during short summers. This idea often surprises people. Greenland feels permanent, ancient, unchanging. But the data shows movement. Ice breathes in and out over time. One of the clearest signals of this comes from oxygen isotopes trapped in the ice. When temperatures are colder, the ratio of certain oxygen types shifts in a predictable way. By measuring these ratios, scientists can reconstruct past temperatures with surprising detail. These measurements reveal that Greenland experienced repeated warm phases called interstadials. During these periods, temperatures rose quickly, sometimes over just decades. Snowfall patterns changed, winds shifted, the ice sheet thinned in places. This does not mean Greenland was ice-free, but it does mean the ice was not always as thick or as stable as it is today. Another source of evidence comes from sediment beneath the ice. In recent years, radar and drilling projects have allowed scientists to study the land surface buried under Greenland's ice sheet. What they found was not a flat, lifeless plain. Instead, there are valleys, ridges, and ancient river channels. Some of these features could only have formed if liquid water once flowed across the land. In 2016, researchers studying sediment from beneath the ice found signs of ancient soil. That soil contained organic material, meaning plants once lived there. The dating of this material suggested that parts of Greenland were ice-free at various points in the distant past. This did not happen recently, but it shows that Greenland's ice sheet has collapsed or retreated significantly before. All of this matters because Greenland sits at the center of Earth's climate system. Its ice reflects sunlight back into space. Its meltwater feeds the North Atlantic. Changes here ripple outward. When Greenland changes, the rest of the world feels it. That is why Greenland appears so often in climate research, and why its ice cores are considered some of the most valuable climate records on the planet. Unlike many unexplained ruins or sunken structures that archaeologists struggle to date, Greenland's ice offers a near-continuous timeline. There are no missing centuries, no broken stone tablets. Snow falls, freezes, and stays. Year after year, storm after storm. Volcanic eruptions leave ash layers that can be matched to known events. Dust from distant deserts settles on the ice and marks shifts in global wind patterns. This level of detail allows scientists to say something rare in ancient history. They can say not just what happened, but how fast it happened. And speed is where Greenland's story becomes unsettling. The ice core record shows that major climate shifts did not always take thousands of years. Some happened within a single human lifetime. Around 14,700 years ago, Greenland warmed sharply at the start of a period known as the Bølling Allerød. Temperatures rose, ice retreated. Then, just a few thousand years later, the climate reversed again. This back-and-forth pattern sets the stage for what comes next. It is also important to be clear about what Greenland was not. There is no credible evidence of advanced human societies living on Greenland before 12,500 years ago. No cities, no temples, no traces of organized settlement like those debated in stories about unexplained ruins elsewhere in the world. Human presence in the Arctic at this time was focused mainly on Siberia and North America, where small groups followed animals and adapted to harsh conditions. Greenland's role in this story is not as a home to ancient civilizations, but as a witness, a silent recorder. While places like Egypt later preserved their past in stone during the Old Kingdom and Middle Kingdom, Greenland preserved its history in ice. No writing, no monuments, just physical evidence, locked in place. This is why Greenland is often compared, in a very different way, to regions tied to ancient mysteries like the origins of Egypt before the pharaohs. In both cases, the question is not what people believed, but what the physical evidence shows. In Egypt, stone and settlements tell the story. In Greenland, it is ice and sediment. As scientists move closer to the period around 12,500 years ago, the signals in the ice begin to change. Layers grow thinner or thicker. Chemical markers shift. Dust levels rise. Temperatures swing more violently. Something is happening in the system. Not slowly, not quietly. By the time the ice cores reach the layers dating to around 12,500 years ago, Greenland's calm record begins to look more like a warning than a diary. The steady rhythm of the past breaks. The planet is about to enter one of the most debated climate events in human history. That is where this chapter naturally moves next, into a time when Greenland's ice does not just record change, but highlights it sharply, layer by layer. Chapter 2. The sudden climate shift at the end of the Ice Age. The end of the last Ice Age did not arrive quietly. It did not fade in over thousands of calm years. Instead, it arrived in sharp turns, sudden drops, and fast recoveries that still challenge how scientists think about climate change. Nowhere is this clearer than in Greenland. When researchers first pulled long ice cores from central Greenland in the late 20th century, they expected to see slow, smooth changes as the planet warmed after the Ice Age. What they found instead was something far more dramatic. Layer by layer, the ice showed that temperatures could fall or rise very quickly. In some cases, the change happened in less than a single lifetime. This period sits near the end of the Ice Age, roughly between 14,700 and 11,700 years ago. It includes a warm phase, a sudden return to cold, and then a final warming that leads into the climate we live in today. The most famous part of this story is a cold reversal known as the Younger Dryas. Before the Younger Dryas began, Greenland was warming. Ice core data shows rising temperatures, increased snowfall, and signs of a climate system moving toward stability. Plants expanded in Europe. Glaciers retreated across much of the northern hemisphere. For early human groups, this warming would have made survival easier, opening new land and food sources. Then something changed. In Greenland's ice, the shift appears as a sharp line. Oxygen isotope ratios drop suddenly, signaling a rapid fall in temperature. This is not a gentle slope, it is a step. Based on the thickness of annual ice layers, scientists estimate that Greenland cooled dramatically in just a few decades. Some estimates suggest major cooling may have occurred in as little as 10 years. This matters because it challenges an old assumption. For a long time, climate change was thought to move slowly, driven by gradual changes in Earth's orbit or slow shifts in greenhouse gases. The Younger Dryas showed that the climate system could flip states quickly, like a switch. The oxygen isotope data does more than show temperature. It also reflects changes in moisture sources and wind patterns. During the Younger Dryas, Greenland received less snowfall, and the snow that did fall carried a different chemical signature. This suggests that atmospheric circulation changed. Winds likely strengthened and shifted direction, pulling colder, drier air into the region. At the same time, dust levels in the ice increased. Fine particles blown from distant land masses settled onto the ice sheet. Higher dust levels usually point to drier conditions elsewhere and stronger winds capable of carrying particles long distances. This tells us the cooling was not limited to Greenland alone. Evidence from Europe supports this picture. Lake sediments show colder conditions. Pollen records reveal that forests retreated and cold-tolerant plants returned. In North America, glaciers that had been shrinking began to stabilize or advance again. The Younger Dryas was not a local event. It was widespread across the northern hemisphere. Yet the strength of the signal in Greenland stands out. Because Greenland's ice preserves annual layers so clearly, scientists can track this cooling with unusual precision. They can see winters growing harsher, summers shorter, snowfall thinner, year after year. What caused this sudden shift remains debated, but the ice itself stays neutral. It does not explain. It only records. After roughly 1,200 years of cold conditions, the Younger Dryas ended almost as abruptly as it began. Once again, the ice cores show a sharp change. Oxygen isotope values rise quickly, snow accumulation increases, dust levels fall. Greenland warms rapidly, marking the start of the current warm period known as the Holocene. This second transition is just as striking as the first. The climate did not slowly recover. It snapped back. Temperatures in Greenland rose by several degrees within decades. This warming allowed forests to expand widely across Europe and supported the spread of human populations into new regions. The speed of these changes is what makes this period so important. Greenland's ice shows that Earth's climate system has tipping points. When certain thresholds are crossed, change can accelerate rapidly. This idea did not come from computer models. It came from ice drilled out of the ground and measured layer by layer. Comparisons with North American evidence deepen the story. Sediment cores from the North Atlantic show changes in ocean temperature and circulation that line up with Greenland's ice record. In the Great Lakes region, ancient shorelines suggest shifting water levels tied to glacial melt and refreezing. The pieces fit together into a broad picture of instability. Still, there are limits to what the data can say. Ice cores do not tell us exactly why these shifts happened. They tell us when, how fast, and how large the changes were. Interpreting the cause requires combining ice data with ocean records, land evidence, and climate modeling. What is clear is that the Younger Dryas was not a minor event. It interrupted a warming trend that seemed well underway. It reshaped ecosystems, altered migration routes, and forced early human groups to adapt once again to colder conditions. For Greenland, this period marks a turning point. The ice sheet responded quickly to climate signals, thinning and thickening as temperatures shifted. The stability seen earlier in the Ice Age gave way to volatility. The ice became a sensitive recorder of rapid change. By studying this sudden climate shift, scientists began to rethink how stable Earth's climate really is. Greenland showed that dramatic change does not always announce itself slowly. Sometimes it arrives fast, reshaping the world before societies have time to adjust. As research continues, Greenland's ice remains the backbone of this story. Each new core adds detail, refining timelines, and sharpening understanding. But the central message remains the same. At the end of the Ice Age, the climate system did not move smoothly forward. It lurched. This chapter naturally leads toward the physical markers left behind by this event, especially the distinct boundary layers tied to the Younger Dryas itself. Those layers raise new questions about what else was happening on Earth at the same time. Chapter 3. The Younger Dryas Boundary Evidence in Greenland. When scientists talk about the Younger Dryas boundary, they are not talking about a story or a theory. They are talking about a thin but powerful line in the ice. A line that appears again and again in Greenland cores, marking a sudden break in Earth's climate history. In Greenland, this boundary sits at a depth that corresponds to roughly 12,900 years ago. It is not labeled in the ice, of course. It is identified through changes in chemistry, particles, and structure that appear almost all at once. For researchers who study ice cores, this layer stands out clearly, even before detailed testing begins. One of the first signs is a sharp change in oxygen isotopes. These ratios, already discussed in earlier chapters, drop suddenly at the boundary. This confirms a rapid cooling. But the younger Dryas boundary is not defined by temperature alone. It is defined by a cluster of signals that appear together. Dust levels increase abruptly. Under microscopes, scientists see higher concentrations of fine mineral particles trapped in the ice. These particles did not form in Greenland. They were carried by wind from distant land masses, likely from colder and drier regions, where vegetation had declined. Stronger winds are needed to move this much dust across such distances, suggesting a major shift in atmospheric circulation. At the same boundary, snow accumulation patterns change. Annual layers become thinner, indicating reduced snowfall. This aligns with a colder, drier climate. The ice does not show a gradual adjustment. It shows a sudden reorganization. Chemical markers also shift. Certain ions, such as calcium and sodium, increase at the boundary. These are often linked to dust and sea spray. Their rise suggests changes both on land and in the ocean atmosphere system. Again, the key detail is timing. These changes occur together, not spread out over centuries. Greenland's ice cores are especially valuable because their layers can often be counted year by year, like tree rings. This allows scientists to see that the younger Dryas boundary is not smeared across time. It is tight, sharp, measurable within decades. Because of this precision, Greenland became the reference point. When researchers study sediments in Europe, lake cores in North America, or marine records from the North Atlantic, they often compare their timelines to Greenland's ice. If a change lines up with the Greenland boundary, it strengthens the case that the event was widespread. One example comes from European lake sediments. Layers dating to the same time show increased erosion and shifts in plant pollen. Forest species retreat, cold-adapted plants return. These changes align closely with the Greenland boundary layer. The same pattern appears in North American records, where glacial activity briefly stabilizes or advances again. Yet Greenland's ice does something those other records cannot. It preserves the atmosphere itself. Tiny bubbles trapped in the ice contain ancient air. By analyzing these bubbles, scientists can measure greenhouse gases like carbon dioxide and methane at the exact moment the climate shifted. At the younger Dryas boundary, methane levels drop noticeably. Methane is closely tied to wetlands and biological activity. A drop suggests that wet environments shrank quickly, likely due to colder and drier conditions. Carbon dioxide changes are more subtle, but the methane signal reinforces the idea of a rapid environmental response. Microscopic particles found at the boundary have drawn particular attention over the years. These include tiny grains of glass-like material and unusual mineral fragments. Some researchers argue that these particles deserve special scrutiny. Others caution that similar particles can form through normal Earth processes, such as volcanic activity or intense erosion. What is important is how scientists handle this disagreement. The ice cores do not say where these particles came from. They only show that they are present and that they appear at a specific moment in time. Interpretation comes later, and it is here that debate begins. Volcanic ash is one possibility often discussed. Greenland ice contains many ash layers from known eruptions. These layers usually have distinct chemical fingerprints that can be matched to specific volcanoes. At the younger Dryas boundary, no single volcanic source has been clearly identified that explains all observed particles. This does not rule out volcanism, but it complicates the picture. Another area of discussion involves the distribution of similar boundary markers outside Greenland. Some sites show comparable dust spikes or chemical changes. Others do not. This uneven pattern fuels debate about whether all signals come from a single global trigger or from a chain of related regional processes. Despite disagreement over causes, there is broad agreement on one point. The younger Dryas boundary marks a real and sudden shift. It is not an artifact of poor dating or incomplete records. The consistency of the signal in Greenland's ice cores leaves little room for doubt about the timing or speed of change. This is why Greenland remains central. When new cores are drilled, scientists check whether the boundary appears the same way. So far, it does. Each core refines the timeline but confirms the larger pattern. Rapid cooling, increased dust, altered snowfall, changed atmospheric chemistry. The controversy surrounding the boundary does not come from denial of the data. It comes from the challenge of explaining it fully. Earth's climate system is complex. Ice cores show what happened, not why it happened. Bridging that gap requires models, comparisons, and careful restraint. For decades, researchers have returned to this boundary because it sits at the intersection of climate, environment, and human history. Early human populations were adapting to warming conditions when the Younger Dryas began. Then the climate reversed, forcing new adjustments. Greenland's ice does not record human response, but it sets the environmental stage with unmatched clarity. As this chapter continues, the focus naturally moves toward how these boundary markers are interpreted and why some explanations gain support while others remain contested. The data itself stays steady. The debate flows around it. Chapter 4: Meltwater Pulses and Rising Seas. As the climate shifted near the end of the Ice Age, the changes did not stay locked in the air or the ice. They moved outward into the oceans. This is where the story of meltwater pulses begins, and where Greenland's role becomes both important and difficult to untangle. For a long time, scientists assumed sea levels rose slowly as ice sheets melted. But as evidence improved, that idea began to fall apart. Coral reefs, coastal sediments, and ancient shorelines started telling a different story. Sea level did not always creep upward. At certain moments, it jumped. These jumps are known as meltwater pulses. They represent periods when vast amounts of ice melted and flowed into the ocean in a relatively short time. Not over thousands of years, but over centuries, sometimes even faster. One of the most studied pulses occurred near the time Greenland's climate record shows strong instability. To understand how researchers know this, it helps to look far from Greenland at coral reefs in tropical oceans. Corals grow close to the sea surface. As sea level rises, corals grow upward to stay in shallow water. When sea level rises too fast, corals drown, leaving behind a clear break in growth. By dating these coral layers using radioactive methods, scientists can reconstruct past sea levels with surprising accuracy. These coral records show that around the end of the Ice Age, sea level rose in sharp steps. One major rise occurred roughly between 14,600 and 14,300 years ago. Another followed later. In some cases, sea level rose several meters in just a few hundred years. That rate is far faster than what most coastlines experience today. At the same time, sediment cores taken from continental shelves tell a similar story. Layers that were once coastal suddenly appear underwater. Ancient river channels are drowned. Shorelines retreat inland. These changes line up closely with the periods of rapid warming and cooling seen in Greenland's ice. This is where Greenland enters the discussion. Greenland held and still holds a massive amount of fresh water locked in ice. When temperatures rise, that ice does not melt evenly. Meltwater can be released in surges, flowing through rivers, beneath glaciers, and eventually into the ocean. Ice cores from Greenland show signs of increased melting during warmer intervals before and after the Younger Dryas. Snow accumulation changes, ice layers thin, and chemical markers linked to meltwater appear more frequently. These signals suggest that Greenland was not just passively recording climate change, it was responding to it. However, it is important to be careful here. Greenland was not the only ice sheet on Earth at the time. Much larger ice sheets covered North America and parts of Europe. The Laurentide ice sheet, which stretched across Canada and into the northern United States, likely contributed enormous volumes of meltwater. Untangling how much came from Greenland versus other regions is one of the main challenges scientists still face. What can be said with confidence is that freshwater input into the oceans increased sharply during this period. This matters because freshwater changes ocean behavior. Saltwater is dense, freshwater is lighter. When large amounts of fresh water enter the ocean, especially in the North Atlantic, it can disrupt how water sinks and circulates. Ocean circulation acts like a global conveyor belt. Warm water moves north, releases heat, and sinks. Cold water moves south at depth. This system helps regulate climate across much of the planet. Fresh water from melting ice can weaken the circulation by making surface waters less dense and harder to sink. Evidence from marine sediment cores suggests that ocean circulation slowed or shifted during periods of heavy meltwater input. Changes in microfossils, temperature-sensitive chemicals, and sediment composition point to cooler surface waters in the North Atlantic at times when ice was melting rapidly. This connection helps explain why meltwater pulses are often discussed alongside sudden climate shifts. The timing overlaps. Rapid ice melt feeds the ocean. Ocean circulation changes. Climate patterns respond. Still, scientists are cautious. The ocean is complex, and direct cause and effect is difficult to prove. Greenland's meltwater likely played a role, but it was part of a larger system that included other ice sheets, changing winds, and shifting temperatures. What makes Greenland especially valuable is how its ice record can be compared to these ocean signals. When melt indicators appear in the ice at the same time as sea level jumps in coral records, confidence increases that these events are connected. Not identical, not perfectly synchronized, but related. Another key tool is isotopic analysis of seawater trapped in sediments. The chemical fingerprint of fresh water differs from that of ocean water. During periods of intense melting, this fingerprint shifts in measurable ways. These shifts appear in multiple ocean basins, reinforcing the idea that meltwater pulses had global reach. For coastal regions, the consequences would have been dramatic. Low-lying areas flooded, river mouths shifted, coastal ecosystems were reshaped. For human groups living near shorelines, land was lost, sometimes within generations. Much of that ancient coastline now lies underwater, which is why the archaeological record from this period feels incomplete. This is where meltwater pulses intersect with broader questions about sunken structures and submerged landscapes. While there is no confirmed evidence of advanced societies being swallowed by rising seas at this time, there is strong evidence that habitable land disappeared quickly. The ocean did not politely wait. As this chapter continues, the focus moves deeper into how scientists model these meltwater events, where uncertainty remains, and why Greenland's contribution is still debated. The data is rich, but interpretation requires restraint. For now, the picture is clear in one essential way. Around 12,500 years ago, ice melted fast enough to raise oceans worldwide. Greenland was part of that story, responding to rapid climate change and feeding fresh water into a system already under stress. Chapter 5: Ocean Circulation Disruption near Greenland. The oceans surrounding Greenland do far more than move water. They move heat. They connect continents. They help decide whether regions warm or cool, dry or flood. Around 12,500 years ago, these ocean systems did not behave the way they usually do, and Greenland sat right at the center of that disruption. To understand why this matters, scientists focus on a large system of currents known as the Atlantic Meridional Overturning Circulation. It sounds complex, but the basic idea is simple. Warm surface water flows north from the tropics. As it reaches higher latitudes near Greenland, it cools, becomes denser, and sinks. That sinking motion pulls more warm water north, creating a continuous loop. This process helps keep northern regions warmer than they otherwise would be. Greenland plays a key role in this system. Cold, salty water near its coast sinks into the deep ocean, helping drive circulation. Even small changes in temperature or salinity here can ripple outward. When fresh water enters this region in large amounts, it can weaken the sinking process. And around the end of the Ice Age, that is exactly what appears to have happened. Marine sediment cores taken from the North Atlantic show clear signs of disruption during this period. These cores contain tiny shells from microorganisms that lived in surface waters long ago. The chemical makeup of those shells reflects the temperature and salinity of the water at the time. Around the younger Dryas period, many of these records show colder surface temperatures and changes consistent with reduced ocean circulation. At the same time, Greenland's ice cores show increased melting during warmer intervals before and after the younger Dryas. Meltwater flowing from glaciers would have carried fresh water into nearby seas. Unlike salty ocean water, fresh water resists sinking. When enough of it spreads across the surface, it can act like a lid, slowing or even stopping deep water formation. This idea did not come from theory alone. It came from matching timelines. When melt indicators appear in Greenland's ice, ocean records show circulation changes not long after. The alignment is not perfect, but it is close enough to suggest a strong connection. Evidence from deep sea sediments strengthens this picture. Changes in grain size, sediment layering, and chemical ratios point to slower deep currents during this time. Some regions show reduced oxygen levels at depth, consistent with weaker circulation. These are subtle signals, but they appear across wide areas of the North Atlantic. Still, scientists approach this carefully. Ocean circulation is influenced by many factors. Wind patterns, sea ice cover, and temperature gradients all matter. Freshwater input from Greenland was likely important, but it was not acting alone. Other ice sheets, especially in North America, were also releasing meltwater into the system. What makes Greenland stand out is location. Meltwater entering the ocean near Greenland goes straight into one of the most sensitive zones for circulation. Even modest changes here can have outsized effects. This is why Greenland remains a focus of modern climate research, as well as studies of the past. Another line of evidence comes from ice-rafted debris found in ocean sediments. These are rocks carried by icebergs and dropped as the ice melts. Spikes in this debris indicate increased iceberg activity, which often follows periods of ice sheet instability. Around the younger Dryas and nearby transitions, such spikes appear in several North Atlantic records. This suggests that Greenland and nearby ice masses were shedding ice into the ocean at higher rates. Sea ice also plays a role. Expanded sea ice can block heat exchange between ocean and atmosphere, reinforcing cooling. Some evidence suggests that sea ice spread further south during colder intervals, further weakening circulation and trapping cold conditions in place. What remains debated is how fast these changes occurred and how long they lasted. Some models suggest rapid shutdowns followed by partial recoveries. Others suggest more gradual weakening. The challenge lies in translating physical evidence into exact timelines. Despite these uncertainties, one conclusion is widely accepted. Ocean circulation near Greenland was not stable during this period. It shifted in response to changing freshwater input and climate conditions. These shifts likely amplified cooling during the younger Dryas and influenced how quickly warming returned afterward. This matters beyond Greenland. Changes in North Atlantic circulation affect rainfall patterns in Europe, temperature swings in North America, and even climate conditions in parts of the Southern Hemisphere. The system is interconnected. As research continues, scientists refine models using new data from both ice and ocean cores. Each new record helps narrow the range of possibilities, but the core message remains steady. Around 12,500 years ago, the ocean system near Greenland entered a period of stress and reorganization. In the next part of this chapter, the focus naturally moves toward how these circulation changes interacted with ice sheet instability and what that interaction reveals about feedback loops in Earth's climate system. Chapter 6. Evidence of ice sheet instability. An ice sheet may look solid and permanent, but in reality it is a moving, changing system. It flows, it fractures, it reacts to temperature, pressure, and water in ways that are not always slow or predictable. Around 12,500 years ago, the Greenland ice sheet showed clear signs of this instability, and those signs are still visible today. One of the strongest clues comes from the shape of the land hidden beneath the ice. Using radar that can penetrate through kilometers of ice, scientists have mapped Greenland's buried landscape in remarkable detail. What they found was not smooth or simple. Beneath the ice are deep valleys, sharp ridges, and wide basins carved by moving ice and flowing water. These features tell a story of repeated advance and retreat. Some valleys beneath Greenland resemble river systems. They branch, curve, and join together in ways that suggest they once carried liquid water. These channels could only have formed if parts of the ice sheet thinned or disappeared long enough for meltwater to flow across exposed ground. This does not point to a single collapse, but to episodes of instability spread across long periods. Ice cores add another layer to this story. In stable conditions, snow falls, compresses, and forms neat, consistent layers. When ice becomes unstable, those layers change. Around the end of the Ice Age, Greenland's ice cores show variations in layer thickness that reflect changing snowfall and melting patterns. Some years show very thin layers, others thicker ones, suggesting rapid swings in accumulation. Chemical signals reinforce this picture. Certain markers associated with surface melting appear more frequently during warmer intervals. These include ions that are carried downward by meltwater seeping through the ice. When surface melting increases, it can weaken the ice from within, making it more prone to cracking and faster flow. This internal weakening is important. Ice sheets do not behave like solid blocks. They behave more like very slow rivers. When meltwater reaches the base of the ice, it acts as a lubricant. It reduces friction between ice and bedrock, allowing the ice to slide more easily. This can speed up ice movement dramatically. Evidence for faster ice flow appears in both modern observations and ancient records. Today, satellites track glaciers in Greenland, accelerating during warm summers. In the past, similar processes likely occurred, though without direct observation. The clues are indirect but consistent. Increased iceberg debris in nearby ocean sediments suggest periods when glaciers were flowing faster and shedding more ice. Another sign of instability comes from ice thickness changes. Models based on ice core data and buried landforms suggest that parts of Greenland's ice sheet thin significantly during warmer phases near the end of the Ice Age. Thinning does not require complete melting. Even a reduction of a few hundred meters can change how an ice sheet behaves. Once thinning begins, feedback loops can develop. Lower ice surfaces sit at lower, warmer altitudes. Warmer air leads to more melting. More melting leads to more thinning. These feedbacks make ice sheets sensitive to relatively small temperature changes. Importantly, instability does not mean total collapse. Greenland's ice sheets survive these changes. But survival does not imply calm. It implies stress, adjustment, and reorganization. The ice responded to rapid climate shifts by changing shape, speed, and thickness. Timing matters here. The signs of instability appear close to the periods of rapid warming and cooling documented in earlier chapters. This alignment suggests that the ice sheet was reacting quickly to environmental change, not lagging far behind it. Scientists are careful not to overinterpret these signals. Ice behavior is complex and many processes overlap. Some changes may reflect local conditions rather than island-wide events. But when multiple lines of evidence point in the same direction, confidence grows. What makes Greenland especially valuable is continuity. Unlike mountain glaciers that come and go, Greenland's ice sheet preserved its internal history. Even when it thinned, it did not vanish. This allows researchers to study instability without losing the record itself. This is one reason Greenland is often used as a comparison point when studying other ice sheets, both ancient and modern. It offers a long view of how large ice masses respond to stress. Not all responses are dramatic. Some are subtle, but together they show a system capable of rapid change. Understanding this past instability matters today. Modern Greenland is warming again. Surface melting is increasing. Meltwater lakes form each summer, some draining suddenly through cracks in the ice. Glaciers accelerate, then slow. These behaviors mirror in smaller scale the processes inferred from the past. The lesson from 12,500 years ago is not that collapse is inevitable, but that stability cannot be assumed. Ice sheets can change faster than once believed. They can reorganize internally long before they disappear. As this chapter continues, attention naturally shifts to how these ice sheet changes interact with the atmosphere itself, especially through dust, ash, and shifting wind patterns recorded in the ice. Chapter 7. Dust, Ash, and Atmospheric Changes. When ice cores from Greenland are sliced open and examined layer by layer, the most obvious features are the bands of white and pale blue ice. But mixed into those layers are darker streaks and tiny specks that tell a quieter story about the atmosphere itself. Dust, ash, particles so small they are invisible to the eye, yet powerful enough to reveal how the skies change during times of rapid climate stress. Around 12,500 years ago, Greenland's ice begins to show a noticeable increase in airborne material. These are not random impurities. They arrive in patterns, rising and falling in step with temperature shifts. Scientists pay close attention to these layers because they are direct evidence of how winds, storms, and dry regions behaved in the past. Dust trapped in ice cores usually comes from exposed land. When climates are warmer and wetter, vegetation holds soil in place. When climates turn colder or drier, plants retreat, soil loosens, and winds lift fine particles into the air. Stronger winds can then carry that dust across oceans and continents. When it finally settles, snow falls on top of it, sealing it into the ice. At the onset of the younger Dryas, Greenland's ice shows a sharp rise in dust concentration. This increase happens quickly, not gradually. The timing matches the sudden cooling seen in oxygen isotope data. Together, these signals suggest a rapid shift toward drier conditions and stronger winds across large parts of the northern hemisphere. The dust itself tells more than one story. Its mineral makeup can be traced back to likely source regions. Analysis shows that much of the dust reaching Greenland during this period likely came from exposed continental areas in Asia and possibly North America. These regions would have experienced reduced vegetation and expanded dry zones as the climate cooled. This means the atmospheric changes were not local. Winds strong enough to carry dust thousands of kilometers point to a reorganized circulation system. Jet streams may have shifted, storm tracks may have changed position. The atmosphere was moving differently. Alongside dust, ice cores also preserve traces of volcanic ash. Unlike dust, volcanic ash has a distinct chemical fingerprint that can often be matched to known eruptions. Greenland's ice contains many ash layers from eruptions across Iceland and beyond. These layers are useful time markers because volcanic events can often be dated independently. Around the younger Dryas boundary, researchers have looked closely for volcanic signals that might explain the sudden climate change. Some ash layers appear near this period, but no single eruption has been definitively linked as a trigger. This is an important distinction. The presence of ash does not automatically imply cause. It only shows that volcanic activity was part of the broader environmental background. What stands out is not one dramatic ash layer, but subtle changes in atmospheric chemistry. Certain ions increase sharply at the boundary. Calcium levels rise, often associated with dust. Sodium levels also increase, which can be linked to sea spray and stronger winds over open water. Together, these shifts suggest a more energetic atmosphere. Methane trapped in air bubbles adds another piece. Methane levels drop noticeably during the younger Dryas. This gas is closely tied to wetlands and biological activity. A sudden drop points to shrinking wet environments, likely due to colder and drier conditions. The atmosphere, land, and climate were responding together. Snowfall patterns also changed during this time. Thinner annual layers suggest reduced precipitation over Greenland. This aligns with a colder atmosphere that holds less moisture. Less snowfall does not mean less ice overall, but it does change how the ice sheet grows and responds to stress. Dust has another effect that scientists consider carefully. Dark particles on ice surfaces reduce reflectivity. When ice becomes less reflective, it absorbs more sunlight, which can increase melting during warmer periods. This creates feedback loops where atmospheric dust does not just record change, but can influence it. Whether this effect was significant at the end of the Ice Age is still debated. The dust levels recorded are modest compared to some earlier glacial periods. Still, even small changes can matter when systems are already near thresholds. What makes Greenland so important in this discussion is consistency. The dust increase appears across multiple ice cores taken from different locations. This reduces the chance that the signal reflects a local storm or isolated event. It points instead to a broad atmospheric shift. Comparisons with records from Europe and North America support this interpretation. Lake sediments show increased erosion at the same time. Lowest deposits made of windblown dust accumulate more rapidly in some regions. These patterns line up with Greenland's ice record, strengthening the case for a hemisphere-wide change. Yet disagreement remains. Some researchers argue that dust sources and transport paths are still not fully understood. Others note that volcanic activity can influence atmospheric circulation indirectly, even without a single massive eruption. The data allows multiple interpretations, and scientists continue to refine models to test them. What is not in dispute is that the atmosphere during this period became more unstable. Winds intensified, moisture patterns shifted. The calm progression out of the Ice Age was interrupted by a system under strain. Greenland's ice captures this moment with unusual clarity. It shows when the air grew drier, when winds strengthened, and when chemical balances shifted. It does not explain why the atmosphere changed, but it proves that it did. As this chapter continues, the focus naturally moves toward how these atmospheric changes fit into the broader picture of human survival and movement near the Arctic during this time. Climate does not change in isolation. It reshapes the world that people must navigate. Chapter 8. Human presence around the Arctic at the time. Around 12,500 years ago, Humans were already living at the edges of the Arctic world, but not in the way many people imagine. There were no cities, no permanent villages carved into icebound land. Instead, small groups moved carefully through harsh environments, following animals, seasons, and narrow windows of opportunity. Greenland itself remains silent in the archaeological record for this period, but the regions surrounding it speak clearly. To understand human presence near the Arctic at this time, researchers look to Siberia, Alaska, and northern Canada. These areas preserve the strongest evidence of how people adapted to cold climates as the Ice Age loosened its grip. Stone tools, campsites, and butchered animal remains show that humans were not merely surviving. They were adjusting, experimenting, and expanding. In Siberia, sites dating back more than 15,000 years reveal advanced hunting strategies. People targeted large animals like mammoth, bison, and reindeer using carefully shaped stone tools and cooperative hunting methods. These groups understood seasonal movement patterns and timed their migrations to match them. This knowledge was essential in landscapes where resources could disappear for months at a time. As conditions warmed during earlier phases near the end of the Ice Age, humans began moving northward. Lower sea levels exposed vast coastal plains, especially in the region known as Beringia, which once connected Asia and North America. This land bridge was not just a corridor. It was a living landscape with grasses, animals, and fresh water. People lived there for generations. Evidence from Alaska shows human presence by at least 14,000 years ago, possibly earlier. Sites like Swan Point and Broken Mammoth contain stone tools and hearts that suggest long-term occupation. These groups were flexible. They hunted, gathered, and adapted their tools as conditions changed. Then came instability. As the climate shifted sharply around the younger Dryas, environments that had been slowly improving suddenly became colder and drier again. Glaciers stabilized or advanced. Plant life retreated. Animals altered migration routes or declined in number. For human groups living near the Arctic, this was not an abstract climate event. It directly affected survival. Archaeological layers from this time often show changes in tool styles and site use. In some regions, evidence becomes sparse, suggesting population decline or movement away from newly hostile areas. In others, people adapted by changing prey targets or mobility patterns. These shifts were not uniform. Human response varied depending on local conditions. What stands out is resilience. Despite rapid climate swings, humans did not vanish from the Arctic edges. They adjusted. Some groups moved south, others stayed but became more mobile, reducing the time spent at any single location. Campsites from this period are often small and temporary, reflecting a need to remain flexible. Greenland, however, remains different. There is no confirmed archaeological evidence of human occupation there around 12,500 years ago. This absence matters. Greenland's environment, even during warmer phases, was still extreme. Ice covered most of the land, resources were limited. Reaching Greenland would have required seafaring capabilities that are not clearly documented for this time period in the Arctic. This does not mean humans could not see Greenland. Coastal groups may have observed it from afar during clear conditions, but seeing land and surviving on it are very different challenges. Greenland offered little margin for error. Some later Arctic cultures, such as the Paleo-Inuit and later Inuit groups, did eventually settle Greenland thousands of years later, using advanced hunting tools and deep knowledge of sea ice. But these developments came much later and under different climatic conditions. What is important here is avoiding overreach. There is no credible evidence linking Greenland to early advanced societies, lost civilizations, or unexplained ruins from this period. The story is quieter and more grounded. Humans were present around the Arctic, but Greenland itself remained largely untouched. Still, Greenland's climate shifts would have influenced human life indirectly. Changes in ocean circulation affected marine ecosystems. Shifting wind patterns altered snowfall and vegetation elsewhere. Rising seas flooded coastal plains, forcing migrations. The land bridge of Beringia itself began to disappear as sea levels rose, cutting off a major route between continents. This flooding was not sudden everywhere, but over generations it reshaped the map. Groups that once lived on now submerged land were pushed into new regions. This helps explain why archaeological records from coastal areas feel incomplete. Many early sites are likely underwater today. The younger Dryas adds another layer of complexity. A return to cold conditions would have shortened growing seasons and stressed animal populations. Human groups already living on the edge had to make difficult choices: move, adapt, or risk extinction. What we see in the archaeological record is not collapse, but change. Toolkits evolve. Settlement patterns shift. Cultural traditions adapt. Humans do what they have always done best. They respond to pressure with innovation. Greenland's silence during this time is part of that story. It reminds us that not every landmass was occupied, and not every challenge was overcome immediately. Some places remained out of reach until conditions, technology, and knowledge aligned. As this chapter continues, the focus naturally turns to how scientists interpret these human responses alongside the climate data, and why caution is essential when linking environmental change directly to human behavior. Chapter 9. Competing explanations in scientific debate. By the time scientists finished assembling Greenland's ice records, ocean sediments, and land evidence, one fact was no longer in question. Something dramatic happened around 12,500 years ago. What remained uncertain was why it happened. This is where scientific debate begins, not because the data is weak, but because it is rich enough to allow more than one explanation. The first thing to understand is how scientists approach questions like this. Climate systems are complex. Ice, oceans, atmosphere, and land all interact. When a sudden shift appears in the record, researchers do not look for a single cause right away. They test multiple ideas, compare timelines, and look for mechanisms that fit the evidence without stretching it. One of the most widely discussed explanations centers on freshwater disruption. As large ice sheets melted near the end of the Ice Age, huge volumes of fresh water entered the North Atlantic. This fresh water, lighter than salt water, could have weakened ocean circulation near Greenland. If warm water stopped flowing north efficiently, temperatures would drop rapidly. This explanation fits well with ocean data and climate models, and it aligns closely with Greenland's location. Support for this idea comes from sediment cores that show changes in ocean currents at the same time Greenland cooled. It also matches what modern simulations suggested could happen if freshwater input increases sharply. However, this explanation is not perfect. Models differ on how much fresh water is needed to cause such a strong response, and exactly where that water entered the ocean remains debated. Another explanation focuses on internal climate variability. According to this view, Earth's climate system naturally oscillates between states. As warming progressed after the Ice Age, the system may have crossed a threshold that triggered a temporary reversal. In this interpretation, the younger Dryas was not caused by a single external event, but by the climate system reorganizing itself. This idea is supported by the speed of the changes seen in Greenland. The climate appears to flip between modes rather than slide gradually. Similar abrupt shifts appear elsewhere in the ice core record, both before and after the younger Dryas. That suggests rapid change is not unique to this event. Still, internal variability alone does not fully explain why the cooling lasted about 1,200 years or why it ended so suddenly. To answer those questions, additional factors must be considered. Volcanic activity is another topic of discussion. Volcanoes can influence climate by injecting particles into the atmosphere that reflect sunlight. Greenland's ice cores contain many volcanic ash layers, and some eruptions coincide roughly with climate changes. However, no single volcanic event has been clearly identified as the trigger for the younger Dryas. Most researchers see volcanism as a background influence rather than a primary cause. There are also ideas involving changes in solar activity. Variations in solar output can affect climate, especially when combined with other stressors. Some studies suggest that solar changes may have contributed to cooling, but the evidence is indirect and difficult to isolate from other factors. Solar variation alone does not appear strong enough to explain the magnitude of the younger Dryas. More controversial explanations exist as well, but they remain debated. Some researchers have proposed that unusual particles found at the younger Dryas boundary point to a rare external event. Others argue these particles can be explained through normal Earth processes like wildfires, erosion, or volcanism. The disagreement here is not about whether the particles exist, but about how they formed. What is important is how the scientific community handles these disagreements. Competing explanations are tested against the same data. New ice cores are drilled. New sediment records are analyzed. Hypotheses rise or fall based on whether they continue to match evidence as it improves. Greenland's ice plays a central role in this process because it provides precise timing. Many debates narrow down to questions of sequence. Did ocean circulation slow before temperatures dropped or after? Did dust increase first or did cooling trigger dust release? These details matter. Over time, some ideas gain broader support while others lose momentum. Freshwater disruption combined with ocean circulation change remains one of the strongest explanations because it connects multiple systems and fits much of the available data. But even this explanation is treated as a working model, not a final answer. This uncertainty is not a failure of science. It is part of how complex problems are studied. The younger Dryas sits at the edge of what can be reconstructed with certainty. Scientists can describe what happened in remarkable detail. Explaining why requires connecting many moving parts. What makes this debate especially important is its relevance today. Modern climate change raises similar questions about thresholds and feedbacks. Understanding how Earth responded in the past helps researchers test how it might respond in the future. As this chapter continues, attention turns to how scientists weigh evidence, why consensus takes time, and what questions remain open despite decades of research. The debate itself becomes part of the story. Chapter 10: Why Greenland's Mystery Still Matters Today. Greenland's story does not end 12,500 years ago. In many ways, that moment is only important because of what it tells us now. The ice that recorded sudden change at the end of the Ice Age is still there, still responding, and still shaping how scientists understand Earth's future. For most of modern history, climate change was imagined as slow and predictable. Ice ages came and went over tens of thousands of years. Sea levels rose and fell gradually. Greenland's ice cores challenged that picture. They showed that Earth's climate system is capable of rapid shifts when certain conditions line up. That realization changed climate science at its core. Today, Greenland is once again warming. Satellite measurements show rising temperatures, increasing surface melt, and accelerating glaciers along the coast. Meltwater lakes form each summer, some draining suddenly through cracks in the ice. These are not theoretical risks. They are observed processes happening now. What makes the past so relevant is speed. Around 12,500 years ago, Greenland warmed and cooled within decades. That tells scientists that ice sheets do not always respond slowly. They can adjust quickly once thresholds are crossed. The ice does not need to disappear to matter. Changes in thickness, flow speed, and meltwater release are enough to influence oceans and atmosphere. Modern researchers use Greenland's past as a test case. Climate models are run to see if they can reproduce the younger Dryas cooling and recovery. If a model cannot simulate what already happened, it cannot be trusted to predict what might happen next. In this way, ancient ice acts like a stress test for modern science. Ocean circulation is a key concern. As discussed earlier, Greenland sits beside one of the most sensitive regions of the global ocean system. Today, freshwater from Greenland's melting ice is increasing. Scientists monitor salinity and temperature in the North Atlantic to see whether circulation is weakening. The past shows that large freshwater inputs can disrupt these systems. The question is not whether disruption is possible, but how much change is needed to trigger it. Sea level rise is another connection. At the end of the Ice Age, meltwater pulses raised oceans quickly enough to reshape coastlines within generations. Today, sea level rise is measured in millimeters per year. But the pace is increasing. Greenland is one of the largest contributors. The past does not provide a direct forecast, but it shows what ice sheets are capable of under sustained warming. There is also a lesson in uncertainty. Despite decades of study, scientists still debate exactly why the younger Dryas began and ended. This reminds us that Earth's systems are not fully understood, even when data is abundant. Greenland's ice record is one of the most detailed climate archives on the planet, yet it still leaves room for debate. That uncertainty is not a weakness. It is a warning against oversimplification. When people look for single causes or simple timelines, Greenland's history pushes back. Climate change is not a straight line. It is shaped by feedbacks, thresholds, and interactions that can amplify or dampen change. Greenland also matters because it is one of the few places where past, present, and future intersect so clearly. The same ice sheet that recorded ancient dust storms and temperature swings is now being measured by satellites and sensors in real time. Researchers can watch processes today that mirror those inferred from the past, such as surface melting, ice acceleration, and freshwater release. This continuity makes Greenland unique. Many ancient climate records are locked in stone or sediment, frozen in time. Greenland's record is alive. It is still being written. There is also a human dimension. At the end of the Ice Age, climate shifts reshaped landscapes, flooded coastlines, and forced human groups to adapt. Today, billions of people live near coasts. Modern infrastructure is fixed in place. Rapid environmental change carries different risks now than it did for small, mobile groups in the past. Greenland's mystery matters because it reminds us that rapid change is not new. What is new is scale. The past shows what Earth can do on its own. The present adds human influence on top of natural systems. Understanding one without the other leaves the picture incomplete. Finally, Greenland matters because it humbles certainty. The ice tells a clear story about what happened, but not a simple one about why. That balance between knowledge and uncertainty is central to science. It pushes research forward without pretending that every answer is already known. As scientists continue drilling ice cores, mapping buried landscapes, and monitoring modern changes, Greenland remains a reference point, a reminder that Earth's climate can shift quickly, that ice sheets can respond faster than expected, and that the past, when read carefully, offers guidance rather than prophecy. This chapter, and the larger story it concludes, does not end with a final answer. It ends with perspective. Greenland's mystery still matters because it teaches how fragile stability can be and how much there is still to learn by listening closely to the ice.